Great. So we were looking at the density, number density of particles under the influence of gravity, right? And we said that we can write down the total flux in two components. One is the systematic drift due to the presence of the external force, and the other is due to diffusion. And in the context of equilibrium dynamics, we made a connection and figured out that we can connect the friction that you get from the fluid to the fluctuation, which gives rise to Brownian motion, which gives us the relation where the diffusivity is related to psi, the friction, in the Stokes-Einstein equation. Okay, and we can sort of rewrite the flux in the following way. So let's write this out in terms of the potential. So what we have would be minus 1 over psi, gradient of the potential times the density. And I'm going to replace dt by the Stokes-Einstein relation, which gives us kBt over psi times the gradient of the density. Okay, that's good. And let's factor out one density out of the whole equation. So what I get is 1 over psi times the number density, then gradient of the potential plus, so I've also factored out the minus sign, so I have plus kBt times the gradient of log n, right? So n times gradient of log n, that's just grad n. Okay, so that's interesting because let's look at this whole expression here and let's factor out the gradient. So I have 1 over psi, the density, times the gradient of the gravitational potential plus kBt times log n. Okay, great. So we can view this two terms, kvg plus kBt log n, can view that as a chemical potential for non-interacting particles. And then if it's at equilibrium, we do not have a spatial gradient of this chemical potential. And that's consistent with the fact that there's no net flux, okay, because the net flux is just minus 1 over zeta n times the gradient of this whole quantity. Okay, that's good. And then a simple question is, what if there's no external potential? Say what happens is 0. Any suggestions on what happens to the density at equilibrium?
It is not during that case that the Maxwell's distribution will not be there.
Yeah, so there's no density gradient. Could be 0, right? Yeah, exactly. So there's no density gradient, which means the density is constant or spatially homogeneous. Okay, that's good. Okay, good. That's interesting. And we can also sort of interpret this flux in the following way.
I see.
So again, let's just manipulate this expression in different ways. So I can write this in the following way. So I just factored out 1 over psi, which is the friction, 1 over the friction coefficient, and then have a force due to gravity. Then I have minus kBt, gradient of log n. So this whole thing times n, right? So notice that this is force. So this thing also has dimensions of the force. Okay, so one can mechanically one may say that minus kBt gradient of log n, so that's a thermodynamic force. So I put that in quotes. So that is responsible for Brownian motion. So that's what's driving the Brownian motion. Okay, so if we write it this way, then we can say that we can write the total flux as the total velocity times n, where we just write the total velocity as 1 over psi. Then we add up all the forces, but also include the thermodynamic component. So we have the external force due to gravity, and then we have this force that depends on actually the density as well. Okay, so that's interesting. So we can then think about a general Brownian particle system. So currently we're looking at essentially a single particle behavior or a dilute system. So what we had, recall that we just have a conservation law of the following form. Okay, so if you look at our degrees of freedom, we just have a spatial coordinate in this case. So n is essentially a function of space x, but also of time. So we can generalize this equation. Yeah, question, yeah.
In this case, when we are talking about this thermal force,
Yeah,
the term which is my KBT gradient of log.
yeah,
So it's the temperature which is there in T, which is playing
yeah,
the gradient of the density of the particle force.
yeah, yeah, exactly. Yeah, 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 yeah. So if you don't have a gradient, then that's not present.
When the thermal part is multiplied by,
Yeah,
it is going to be getting a weight
that's right.
coming from this gradient of log.
Exactly, exactly, yeah. Other questions, comments?
Okay, anyway, we can understand it, how what is happening. One thing is clear that is the first case when you said that gravitational potential is zero, it's kind of vacuum condition.
Yeah,
In the space.
yeah,
So all the particles distributed uniform.
yeah,
So that's quite obvious.
right.
But but in this case, when we are talking about this minus KBT,
Yeah,
gradient of log n, why this factor is coming in case? This large factor of what causes this to be multiplied by this KBT?
yeah, so, yeah,
KBT is energy.
that's true, that's right, yeah.
It force.
Yeah, so you say, in terms of the units, you have to divide by a length. That's coming from the gradient. So that scale is set by the variation on log n. Yeah, but you have to think about where the density comes from. If you, yeah,
FT is the force.
yeah,
KBT is the energy.
that's right.
How they are considering?
Because you have a gradient, spatial gradient that has 1 over the length. So dimension-wise, yeah, right. So gradient is 1 over length. So energy divided by length, that's dimension of the force. Yeah,
Distance is coming.
yeah, yeah,
Yeah, so
yeah, yeah, yeah. But the density gradient is in this context is actually set up by the external force. So if we wouldn't have it, then the density gradient goes away.
come from where?
Sorry?
That is solar forces come from where?
Yeah, in this context, that's coming from gravity. Yeah, yeah. Other comments? Okay, so we looked at a single particle, and essentially we have one sort of coordinate, which is space. And we can generalize this equation to look at a general system with, say, n degrees of freedom. So that's called the Smolkovsky equation, which is essentially a generalized conservation law. Okay, so let's consider a system with potentially n coordinates, x1, x2, all the way to xn. And I'm going to use a shorthand with the bracket x to denote these coordinates. So these would be the set of dynamic variables that describe the state of the system. Okay? So in the simple case where we look at a particle under gravity, what we had is, the velocity of the particle due to the gravity is just 1 over zeta times the force. Yeah.
The disconnect.
I haven't touched it.
No.
Oh, okay. Maybe I can unplug and plug again?
Oh, yeah, this way, because the Google Meet is not on it.
Okay.
Should be a bit.
Apparently,
I think this thing took over both screens. Oh, it's coming back. It's coming back. Oh, good.
On both.
Okay, suppose we have n coordinates, and we call these dynamic variables, and that can describe the state of the system. So in the case of one particle, what we have is just the following relation, but in general, we can have the same kind of relation, but generalized to more coordinates. So if we think about the nth coordinate, say the velocity for the nth coordinate can be written as, in general, a sum of Lmn, sum over m. So I explain what L is in just a moment. X, so that depends on the configuration of the system, times an external force, say, applied to the mth coordinate, F of m. So an example is a multi-particle system. So I have particle 1, particle 2, okay, and all the way to particle n. So these x's can be their position. Say x1, x2, x3, and so on and so forth. If you think about these particles that are embedded in a fluid environment, say if you apply a force on particle n, that causes particle n to move, which generates disturbances in the fluid, which will then affect other particles, right? So which means that's why we have this sum. So when you have a force on particle m, that will induce a velocity on all particles in general. And this L here is just a generalized mobility matrix. In the case of a single particle, that's just 1 over zeta. But in general, it will be a matrix coupling all these coordinates. So L here.
So can you please extend the matrix?
Yeah. So I was talking about a single particle where you apply a force, right, you get a velocity that's just on your own. If you have n particles in a fluid, a force exerted on particle n will induce a disturbance flow in the fluid, which affects the motion of all other particles. So L and M here, essentially that explains the coupling. That's the mobility matrix for a n particle system or a system with n general coordinates. So the example we looked at is a multi-particle system in a fluid. Okay, so in this case, if you're thinking about multiple particles in a fluid, this mobility matrix is going to be determined by hydrodynamics. Which means that in general, you want to resolve the fluid mechanics that's happening when you have n particles, and then from that, you decide what the mobility matrices are. So for now, we're just going to leave it as is for now, and then we're going to try to generalize our one particle equation into an n particle equation. So let's define, as we did before, a density or a probability distribution function. So let's call that P, which now depends on all these coordinates and time. So that will be the probability density function or PDF. So that's the probability density function of finding the system at a configuration X at a given time t, right? At a particular configuration at time t. Okay, that's just a direct generalization of the one particle density function to an n particle or n coordinate system. So this quantity is conserved, just like the one particle density function, which means that we can write down a conservation law for P. And in this case, we have n coordinates, so we just have to sum up all these fluxes or currents. So we have the gradient with respect to the nth coordinate times the flux in that coordinate. So that's, again, adds up to 0. That's a general conservation statement. Any questions up to this point? Okay, great. So then, from our previous discussion moments ago, we can write down the flux for the nth coordinate just by writing this as the total velocity that you get from that coordinate times the probability density function, as we did for the one particle behavior. So then the only difference here really is in the mobility. So then the total velocity can be written as, now it's a sum because we have more than one coordinate, over these mobility matrices. That's multiplied by, so you could have an external force applied to M, and you would have the Brownian part, kBt, gradient of the nth coordinate, log of P. So that's a direct generalization of the one particle equation that we looked at. So what's happening here? So essentially we have interactions among x, which leads to the fact that, for example, a force exerted on a particle m will lead to a motion or a response on particle n. Okay, any questions? Okay, great.
So we answer.
Yeah.
The response is done here.
Yeah, so you would have a response from all the coordinates in general. Yeah. Whether it's a n coordinate system or you're literally thinking about n particles, right, in a fluid. Yeah. So here we're writing this in a general way. So you can, if you want to visualize this, you can think about x as n particles. Each particle has their own coordinate in space, right? So I mean, the interaction, what I mean is when you have a force on n, you get a velocity on another particle. That's what I mean there in terms of the interaction. Yeah, because there's fluid around. Yeah. Yeah, there's fluid, particles are all embedded in a fluid environment. That's why.
Exactly what.
Exactly. So it's mediated by the fluid. Yeah.
This is just the vector position of the.
That's right. You can think about it that way, but this is a general formulation, right? So it doesn't have to be n particles. Can be a particle, or you can have a connection of particles that have some constraint on them, but nonetheless, it's essentially just all the coordinates in the system that you have. Yeah. Good. Other comments? Okay, great. So let's, again, consider a simple example. We don't have to necessarily have n particles. We can have one particle, for example, a particle that's not spherical. So to specify the configuration of this particle, we have to do two things. One is to specify, say, the location of its center, for example, for an ellipsoid. So that would be x. But that's not sufficient. We need to specify the orientation of this ellipsoid as well, right? So we can do that by attach a body fixed vector to this ellipsoid. So these two coordinates would define the configuration of this ellipsoid at a given time. Does that make sense?
Yeah.
Okay, great. So then we can write down in this case, just a single particle probability density function, P, but it depends on both the position, because specifying the position is not enough to specify the configuration of this particle. So we would also specify what's the orientation at a particular time. So that would be our PDF, describing a single particle. Non-spherical in this case. Okay, and then we can write down a conservation law for P as we did. So the first coordinate is just position space, gradient, times a flux in this coordinate. I'm going to call that the translational flux, so because that is literally the physical space. But there's also a gradient in the Q coordinate, so I'm going to call that a rotational gradient. Then there's an associated rotational flux. Okay? So the translational flux, we can write this down. So that's given by the 1 over the friction. So in general, we can write that as the mobility matrix times the external force and the Brownian part. So maybe we have external force, then we have the Brownian part. Similarly, the rotational flux, we can write down in the same way. In this case, it's just the mobility in the orientation space for angular coordinates. So that's coupling the torque to the angular velocity. So if we apply external torque, then we would have this term. Then similarly, grad R of log P. Okay, so we see that even to define a single particle that's not spherical, if you want to keep track of the orientational degree of freedom, you have to specify that as well within your probability density function. Any questions or comments on this?
This is why we intensive where we must string KPT with it. Like if you don't consider the dimensions of all these.
So I've essentially what I've done is I've factored out that term. So we'll have to go back here.
What is it like typically? How can we understand what KPT is?
So KPT is the thermal energy, right? So in this case, we're trying to interpret this at the same level of F, which is in this case, that's the gravitational force, right? So conceptually, that looks like a force term. So that's the thermal energy times the gradient of the log of the configuration. It has dimensions of the force, but it's really for convenience. So what you want to do?
Coming in, can we take something as because of the thermal agitation?
Yeah, because the density gradient drives up the motion of the particle, right? And that's said by two things. One is KBT, the thermal energy. The other is the gradient. Yeah. So from the outset, what we have is this, right?
We can go from
Yes.
this dt.
Yeah, I've just replaced dt by kBt over zeta, and then I've factored out zeta.
We can directly go from this.
Yeah, you can just use dt instead of kBt. So if you do that,
Also, I want to
yeah,
how are defining it as much over.
we're still looking at Brownian systems. We haven't talked about active systems yet. Okay, make sense?
Yeah.
Okay, great. So there's a mathematical complexity here. So x, that's just the position coordinate, okay? We know how to take gradient with x. That's fine. So the question is, how should we write down the orientational gradient or the rotational gradient? So right now I've represented that symbolically using grad R, right? But what is it? How do we operate this? How do we define this? So that's something we want to think about right now. Okay, so to do that, let's think about a particle like the one we're looking at, which has a body fixed coordinate. So if I apply an external torque on this particle, I'm going to rotate it, okay? So let's consider this. So consider a torque. I'm going to call that an external torque, L, that's exerted by an external potential. Say, let's call that V. So this potential is only in the orientation space. So that's a function of Q. So we can consider a small rotation of the particle configuration.
Anyway.
I'm going to call that delta psi. So that's a small rotation. So this small rotation will change the orientation of the particle slightly from Q to something else, right? Q to Q plus delta Q, right? So, but there's a relation between delta. So for convenience, let's write delta Q as the following, as delta psi and cross product with Q. The reason is Q is a unit vector. It only represents the orientation. So if you rotate Q, you can't change the length of Q, right? Which means the rotation is normal to Q. So that's what this delta Q is. So if you take a cross product Q with delta Q, that vanishes.
Again.
So the way to write this, so instead we can write it in the following way. So it's Q plus delta psi cross Q, which already embedded the fact that this rotation doesn't change the length of Q. It's only rotating Q. Okay, does that make sense?
Good.
Okay, great. So, well, so what we have is then, when we apply the external torque for this change, it's going to do some work. So the work needed for this change, so that's given by the torque times delta psi. So this has to be equal to the change in the energy, potential energy. In V, which is V Q plus, so the new energy is Q plus delta psi cross Q minus V at Q. Okay, so let's figure out what's this change. Because we're looking at a small change in configuration, we can do a Taylor expansion of the first term around the coordinate Q. So let's try that. So let's take this term here and then do a Taylor expansion.
Okay.
About Q. So let's try that. Then what we have is V at Q plus delta psi cross Q. That's equal to V at Q. Okay. Plus the difference, which would be delta cross Q dotted with the derivative of V with respect to the vector Q, right? It's a Taylor expansion. So there are higher order terms which would be on the order of delta psi squared. Okay?
The directly we're considering at Q with
Q is a vector. It's a derivative with it.
derivatives. This derivative. We're considering it at Q.
Yeah. So it's all, yeah, this is evaluated at Q. That's right. Yeah. Okay, good. Then the difference So notice that if I put this back into this difference, I'm going to cancel out the term, the first term, as one might expect. So then you can take the limit as delta psi goes to 0. Then what you have, first let's write this down. We have that's equal to the difference, which gives us delta cross q dotted with dv dq. Okay, let's evaluate at q plus, again, higher order terms, which we don't care about. So which means we can write this in the following way. So we can have L will be equal to minus grad R of V, so long as we define grad R as Q cross the derivative with respect to Q. So what I've done here is I've made use of a vector identity, so you can swap the order of the cross product with the dot product in a certain way that wouldn't change the sign. So in this case, that gives us delta psi dotted with Q cross Q, okay, at Q. And then equating both sides means that we can write it this way. So that's one way to write the rotational gradient operator. Okay, so that's great. And then, okay, so going back to this particle, we're looking at a non-spherical particle. The question is, we can still making use of this same framework to describe a spherical particle. But what happens in general is why don't we talk about the rotational dynamics of a sphere? So
This with the
yeah,
writing Q vector. Q is the orientation.
so yeah, Q is a unit vector that's attached to the body. Yeah.
Then there is the unit vector called subsidiary. Yes, that orientation is described hooks up the either angles.
Sorry?
Either angles.
Yeah, you can do that.
So,
Yeah.
that's how we understand the orientation.
Yeah, so you
Because
yeah.
The director or the orientation, body fixed orientation of the particle
Yeah.
can only be written in terms of those three either angles.
Yeah, yeah.
So when you are talking about this gradient,
Yeah.
we have defined gradient for rotational part
Yeah.
as Q class del by del Q. How we are going to take care of the three either angles part? We don't have to do that.
Right now we're writing this sort of in a tensor invariant form. So if you write down, you can write down this operator in Euler angles. Yeah.
This is in a closed form, it's okay.
Yeah.
But when you go for the application part,
Exactly.
so there
You have to write out
we have
the
to-
coordinates.
We have to break it.
Yeah. Yeah. Which I'll
Each and
yeah.
every,
Yeah.
angle part.
Yeah. Exactly. Which I'll do later on. So the utility of this one is it applies in both say 2D and 3D, right? So for general derivation, we'll make use of this operator. But if you want to actually say, I want to solve the equation in 2 dimensions, then we just need one angle in 2D.
Yeah.
And then we will sort of write down what this would be in 2D. And then it's just an angular derivative, which you will work out. I'll show you that later on today. Other comments about this? Okay, great. So let's again go back, reduce our problem once again to a sphere. Yeah, you would have, say, spherical polar, you have theta and phi, for example, right?
Is replaced by the theta?
Yeah, but you have cosines and sines there, right? The trigonometric functions in front of the derivative. That's why you have q. So the rotational gradient actually depends on the coordinate. So there's a prefactor, right? Whereas the spatial gradient is, as you said, is simple, just a simple partial derivative. Yeah. So that's why we did this exercise. So this is a sort of a general invariant way of writing it, whether it's in 2D, 3D, or however dimensions you want. But later on, we'll specialize this to 2D, for example. So right now, we want to think about a sphere. So we can take this model, and then the question is, what happens for a sphere? Okay, we can still write down the same equations. Okay, so suppose we have a sphere. You can sort of dye half of the sphere, color it, and then you can attach a body fixed vector to it. But then the point is, your equation
But tiny.
so imagine you have a Brownian particle sphere, and then you dye part of it so that you can track its rotation, right? That's only for visualization of the orientation. You can still attach a vector to it in that sense. You can still write down the same equations. But then the question is, normally we don't care about it, because for a sphere, if we think about the density n, so what is the density? The density would be, so notice that P describes both the position space and the orientation of the particle. So if I were to integrate out the rotational degrees of freedom, what do I get? I get a distribution function only in space, and that's the number density, right? So therefore, we see that actually the number density is just a marginalization in the language of probability. So I'm just going to integrate out all the rotational degrees of freedom, and then I get my number density back. Okay, so let's try that here. So the first term, I'm just going to carry out the integration within the.
So for the case of spherical particles,
Yeah.
you are able to associate with a different vector,
Yeah.
whereas it is typically
Yeah, you could just color part of the particle, and then you can track the orientation.
there is no color.
Yeah. Yeah, but that's only for convenience, right? Visually, if you want to track it, you have to be able to visually have to be able to know whether the sphere is rotating or not. Yeah.
Go up.
So okay, so let's try to integrate out this equation to get an equation for the density. So I'm integrating in orientation space. So if you look at the second term, I can swap the order of the spatial gradient and the orientational integration. So I would get something like the following. Right? Okay, that's fine.
Right.
But then I have this integral, which I have to do. Okay, so I don't know how to do that. So there's some more math involved with orientational operators. So let's try to think about how do we carry out this integration in orientation space in general. So the way to think about this, the way I find the easiest is to think about a unit sphere of orientations. So I have a body fixed unit vector that describes the orientation of a particle, right? Which means for each unit vector q, I can associate a point on the unit sphere. That's exactly a one-to-one match between q and this point, right? So for example, my orientation is this way. Then the point here on the unit sphere represents my orientation. So there's a one-to-one map between that q and the point on the unit sphere. Does that make sense? Any comments?
So
Yeah.
starting point the sector of a sphere.
So Q is I know this sphere here is not the particle, that's just the representation of the orientation space Q, right? Q is a unit vector that, if you're imagining in 3 dimensions, then Q can go whichever direction. But the point is, for whichever Q that you're looking at, there's exactly a point on a unit sphere which corresponds to that Q, right? Because you can just draw it like this. So you have a Q vector here that's sort of starts from the center, right, of the sphere, and then in whichever direction Q is, there's 1 point on the sphere, exactly 1. Does that make sense?
Or we have this, like, they come with X.
Yeah. Or you can think about parameterizing Q in 3-dimensional space using the spherical polar coordinates. Then you would have 2 angles, right? The polar angle and the azimuthal angle. But what does these 2 angles give you? Gives you 1 point on the unit sphere, right? For a given theta or phi of these 2 angles, you find 1 point on the unit sphere. So that would be your representation for Q. So what we can do then in this way is, so let's embed Q
Ready.
in a Cartesian space. X, I call this capital X. That's different from the position. So I'm just representing Q space now. And what we can think about is, if you think about the gradient with respect to this capital X, which is now a normal Cartesian space. So I'm going to write that this way. Other comments about this? I can break this apart into 2 components in a spherical coordinates. One is the derivative in the Q direction. Again, that would be in the radial direction, right? Problem once again to a sphere. So that's what's the vector in the radial direction? That's Q. And then I have a derivative in R. So R would be my polar
when we
coordinate.
write a gradient,
my radial coordinate.
For the spatial part,
And then
we just write
what's left is the derivative with respect
summation
to
of
Q.
del by del x. Okay.
Yeah.
So there are 3 special parts: del x by del x, del by del x plus
Any
del by del y
questions
plus del by
about
del z.
this?
So that makes the only
which
thing
part?
which comes in the
What is
picture.
Q that kept
Now what he has done actually,
This one.
he has
So I'm
written
writing,
down an
let's think about a
expression
3-dimensional
for the
space,
gradient
okay?
of
And
the
then have a
angular.
unit sphere.
Yeah, so it turns
within
out,
that
yeah,
space.
exactly. The
If I
angular
take a
gradient is
normal Cartesian
non-trivial.
gradient,
Angular gradients is now
in a
having
spherical
a form
polar
which is
coordinate,
Q
I would
cross
have
del by
a
del Q.
radial coordinate R.
And this Q
Right?
itself is involved.
So what you do is
Yeah.
then you write
But in a
write
closed
the
form, we can,
Cartesian in that coordinate, the
it's
gradient
like-
in that coordinate, you would have R gradient, but that's in the R direction. What's the director in R?
The director is already,
Q. So that's Q times partial R, right?
but that is a vector B too.
Yeah, that's the second part. So this is the first part. That's the radial derivative. And then all that's left is angular derivatives. So that's the gradient with respect to Q.
That plotting it by a dog unit sphere about this. Why we call it and what it
Because the rotation vector, we've constrained its length to be 1. Yeah.
but if it
So we don't want to deal with the fact that it's really for convenience, because you could, in principle, you could use a vector of length 2, for example, to represent your orientation. Right? That doesn't change the fact that you're still representing the same orientation, but then you would carry the length with you, which will be messy. So we just take a unit vector instead for convenience. Does that make sense? Because we just need a vector to represent the orientation of the particle, right? Whether you take a vector of length 1 or length 2 or whatever.
orientation of a point on the sphere.
Right now, yes, but in the original representation, we're looking at the particle orientation, right? Using Q to represent that. Yeah. And we've taken the assumption that we're taking Q to be unit.
The spherical.
Yeah.
Okay. But if the particle is fixed,
Yeah.
choose a frame of reference.
Uh-huh.
You can associate angles with each and every point.
Sure. Yeah.
The sphere is stay moving.
Yeah.
Okay, rotating.
Yeah.
If you focus on each particle physics, then we can say that so it isn't change.
Yeah.
It doesn't make any difference because if it is in the symmetrically rotating,
Yeah. So you can.
all points are equal.
That's right. Yeah. You just have to be consistent of what reference are you using. That's all. Yeah.
But what my confusion is that in the case of spherical particle with
Yeah.
then associating an orientation
Yeah.
very useful.
Yeah.
But if the sphere is something which is not,
It's not. Yes. It's not useful. Yeah.
then its usefulness is something which is Taiwan for.
Yeah. So that's not useful right now. I'm trying to use that to motivate sort of the calculation of how do I calculate this integral, and then later on, I'm going to use that for active particles. where even for a sphere, okay, for a spherical particle that's now active, even though geometrically the orientation is not important, but because you're swimming, when a spherical particle is swimming, it has to swim in a certain direction, and then we're going to use a vector q there to represent sort of the swimming direction of a sphere.
In that case,
Yeah,
saying, case of H,
yeah,
maybe some sort of asymmetry in the environment.
yeah,
Like, for example, the
yeah,
color,
yeah,
color is creating the asymmetry.
yeah,
Just like that, there's just the label happening with it.
yeah, yeah,
When you are talking about the spherical party, which is identical
yeah,
in all directions,
yeah.
within the medium where gets the activity,
Mm-hmm.
with that some sort of asymmetry is created,
Yeah.
also which it is, and then it is meaningful to.
Yes, exactly. Yes, yes.
Right now we are doing an exercise
Yeah, we're trying to figure out how to.
which will
Yeah,
move
that's right.
in that situation.
That's right. Yeah. So now it's an exercise to get the integration done. So then what we set out to do next is to, for convenience, of course you can write out all the angles and try to carry out the integral. That's one way to do it. Say in spherical polar coordinates. Right now we're just writing this in a vector annotation. So then we can relate the gradient in orientation to the Cartesian gradient, but then we have to subtract off the part that's the radial gradient. Okay? Yeah.
This is the Cartesian gradient. The radial gradient is different.
The radial is this one here.
But no, I'm not.
Yeah.
I was just saying, this is this. Yeah.
So I'm writing the spatial gradient in a spherical coordinates, if you will.
For this, like that grad of R.
Yeah. Which are?
You have defined grad of R basis.
Yeah. So that's this, right? So I'm getting to that. So right now what we're trying to derive is a
The Q of 180.
Yes. So what we're trying to do here is we're trying to derive a formula to carry out integrations like this. Okay, so that's what we're trying to do. And then I'm going to make use of this quantity here to do that. Does that make sense? Any other questions? Okay, so let's do a 2D exercise. How about that? That would be much easier to understand. So let's think about 2 dimensions. So in 2D, then what we can do is, we have a orientation vector q. We can parameterize q using a single angle, say with respect to a Cartesian coordinate x and y, right? So that's angle, say phi here. Then I'm going to also, so then essentially you can write q as cosine phi, sine phi, right? In a vector notation. So let's see what we get for these things. Okay, great. So let me redraw this again. So we have a Cartesian frame of reference, x and y. So we have our vector q, which we've parameterized with an angle phi, right? So what is this? The derivative with respect to q. So how can we change q? We can only change q by change phi, right? So then the derivative is with respect to phi. However, this is a vector gradient. So what is the direction of this change? What is the direction of q as it changes? So it's normal to q, right? So that would be in this direction. So then in a polar coordinate, let's define a vector in this direction as e of phi. So let's say e of phi is a unit vector in the phi direction. Okay? Does that make sense? Okay, great. So then our grad R would be q. So then which means here we would associate this vector e phi here. Okay? And then what is q cross this derivative? So that would be q cross product with e of phi, right? And then the angular derivative. What is q cross e phi? that's in the third direction, right? So let's call that the z direction. So then this becomes Ez. Okay? So then this guy is the unit vector in the z direction.
Working.
Okay, does that make sense? Any questions, comments on this? So then if we think about, say, an orientational Laplacian, then we can write that as grad r started with grad r, right? Times p.
Okay.
So what's that going to be?
So see, here it's very interesting. It's that, good example, it's obvious that this the wavelength,
Yeah,
when something is rotating on this,
yeah,
the gradient is coming out.
right.
So it's like opening the gap.
Yeah,
This
exactly. Because you have only, there's only one way. Yeah,
the movement is in.
yeah. It's out of the plane in 2D. Yeah. So it actually naturally emerges. The vector is in the z direction. So then if you take the Laplacian, right, then you just get the second derivative. Does that make sense? Okay, so in 2D, it turns out it's quite simple if you write it out in the angles. So later on, we'll also do 3Ds in 3 dimensions. So that will be just slightly more complex, but the spirit is the same, right? In 3D, you would have 2 angles now in the spherical polar coordinate to represent that. So now coming back to our calculation, what we want to do is we want to say, how do we integrate grad r dotted with, let's say, a general vector f, which is a function of the orientation q, dq. So in 2D, we know how to do that now. So grad r is in the z direction, right? And then partial phi, then dotted with f. So what is, okay, dq. So what is dq in 2D? Any suggestions? Again, look at the sketch here. So how does the exactly? So dq is defined, right? That's the volume element.
It's an init sphere. With not init sphere, we know where it's RC.
Yeah, so that's why you don't want to have that with you, because then it's messy, and also it's not useful to have a vector with non-unit length, because we only just care about the direction, not the magnitude of the vector. Okay, good. So then here was the z vector is a constant, has nothing to do with the integration. So we just have, I guess, Ez dotted with f. Okay, so then integrating in phi goes from 0 to 2 pi. In 2D, I guess there's a derivative that I've missed here. Okay, sorry. Phi derivative, d phi. So what's that going to be? Right? But a function of the orientation space is periodic.
That's right.
Because the orientation doesn't matter how many revolutions you take. So angle 0 is equal to angle 2 pi. So this actually is 0. So that's good, because what we're trying to calculate is we want to reduce the full equation into an equation for the number density. But we know what the equation for the number density looks like. It doesn't have the rotational part, so that's actually 0. So we're just left with the equation, which is okay, equal to 0. And then for a sphere, we know what this looks like.
I have a question.
Question, yes.
That when this goes to 0,
Yeah, this one, yeah.
it's the film going here.
No. because we've constrained this to be in orientation space. Yeah, whether it's 2D or 3D, in 3D, mathematically, to describe the periodicity is a bit more tricky, but the symmetry is still there. So it wouldn't be non-zero.
So for spherical particles, or
No, it has nothing to do with part. It's just doing calculus with the angles, right now. Yeah.
I'm just saying that then if it comes to be zero, then it doesn't have the value in the equation, right?
Yeah. Then the question is, where does activity come from? What does it imply for active particles? So I'm trying to build up these puzzles for you, and then we're going to look at what that means for an active particle. Does that make sense? Any comments on this? I think that's a very good observation here. Okay, so let me carry through this calculation here. External force, right? Okay. So the external force here doesn't depend on the orientation. Then if we do this integration, what we get is just 1 over zeta force number density minus the diffusivity times the grad of the density. So that's what we had in the outset for a particle, where we're only tracking the spatial gradient. Okay, any comments on this? So let's now think about an active Brownian particle and see what's the difference with what we just did right now. So active Brownian particle. So that's a model, or one of the simplest models for active particles. So what does this mean? So let's think about a real active particle or an active entity, for example, a microswimmer, something like this. Okay, so it's a microorganism.
What?
Right. So this guy is swimming around. And so that's a real organism, and we're going to model that as a particle. For now, we're not going to worry about the non-spherical geometry of the microorganism. We're going to take a spherical particle as the simplest model. And what we say is, because these particles, they're swimming, so why don't we associate a swim velocity for them? So let's define, say they have a speed us, that's a swim speed of these particles. Well, when you talk about a swim speed or a self-propulsion, you have to tell also, yeah.
We can take
Oh, yeah, okay. Let's take a 5 minute.
T is out.
Oh, okay.
So after that, we can start this.
Yeah, that's fine. That's good. So let's take 5 minutes or? Okay, let's take a 5 minute break then.